Welcome to our session today, Scaling CPU Experiences and an Introduction to the Entity Component System. I'm happy to share this session today with Mike. So pretty cool that he is here, and we're really looking forward to his part as well. So we kind of share this session a little bit. He will have the major part, talking actually about the introduction of the Entity Component System. And my part will be, I have the opportunity to talk a little bit about Intel, but no worries, I don't want to sell you some CPUs today. That definitely don't make sense on this stage. I just want to give you a short overview about what Intel is doing in the community of game developers and why we think that there is a good fit between Intel and of you guys. But first, let me introduce myself a little bit. I will keep it very brief because it's not about me today, and it's also not about Intel. I'm a developer marketing manager at Intel. We are responsible for game developer programs like the Intel Buzz Workshop, for example, and also we are very active in the AI sector. I'm located in Munich, so I'm German. I'm definitely a gaming and technology lover and enthusiast, as probably all of you as well. And that's the first big part. Please feel always free to contact me via LinkedIn or via mail or contact Intel. It's absolutely no problem. We, as a company, we as Intel, we don't want to be the big company in this. We want to be part of the community. We want to be equal partners. That's very important. That's why please feel always free to ask me questions afterwards about technologies, about the strategy, whatever you want to, feel free to connect with me. Intel Technologies. As I said, I don't want to sell you some stuff today. So the next slide will just be a short overview of what we have, what our products are, what you can develop your games on. I think the lot more important part is that we don't just want to sell it to you and then leave you alone. Definitely not. We want to do more. We want to support you afterwards, and we want to help you to create something great. That's why we say, let's work together to shine together. And that's another very, very important part why I think that you also can benefit from our Intel technologies. Because right now we have an 81% market share of the total GPU market. And before you guys throw stuff to me, yeah, I'm talking about the total GPU market, including integrated graphics and all of the other stuff. But that's exactly the perspective I want to give to you. Because gaming is going crazy right now, and that's cool. Gaming is ready for mass adoption. It's becoming mainstream. And that, I mean, it sounds a little bit negative, but it's a pretty cool thing. Actually, it's a pretty cool thing. Because making a game ready for mass adoption, making it ready to play for everyone, means you have the opportunity to get a lot of revenue. And for me, you guys are artists. Creating a game is kind of an art, right? But every artist needs kind of a freedom to be creative. And this freedom can be given by you with the help of revenue. I saw many of really, really good games, which weren't able to be played by everyone out there, and it simply wasn't a success. So what I want to tell you is, if you enable and optimize your game for Intel technology, for CPUs, and for integrated graphics, and that's why also the Entity Component System is a big part, and that's why we think sharing the session with Mike definitely makes sense. Then your game will be playable for everyone, and that's a very cool and good thing. There are hundreds of million potential users out there right now who are playing games. And now, as enthusiasts, as we are all, we probably sometimes live kind of in our own world. I mean, it's still a cool market. 60 million people or more. But we have a potential market out there, hundreds of millions of people playing games right now on their normal laptops with an Intel CPU and with integrated graphics. So optimize and enable your game for that technology, and you will have freedom to create something great. And even if you're not that much into creating a game for the mass, still be aware that there is 17% of Steam users out there playing on integrated graphics. And there are 17% of Unity users also using integrated graphics and CPUs. But I think you can also benefit highly from enabling and optimizing your game for the CPU in very different key areas, like, for example, the wind, the close, background life. All these key areas of game developing can be improved if you enable and optimize your game on the CPU. And that's why I'm also really looking forward to Mike's presentation shortly, because it's a really cool thing. As I said, we want to do more, we want to support you, and we want to shape the future together. And I mean, wow, that's a very strong words, I know. Shaping the future together. But imagine we are living in such awesome times. I think no other human have ever before so many opportunities to create games. That's because we have so awesome technologies coming up right now, AI and all the other stuff. So let's take advantage of these and let's shape the future together. And as I said, we from Intel, we want to do more. And that's why we created some buzz workshops, some game developer programs, but also the Intel Game Developer Zone. So that's kind of a platform for the community where all of you can come together, exchange your experiences, or ask us some stuff, get rid of bugs or whatever, and also use some of our tools we have for you. And it's all for free. I mean, we have tools like the Intel Graphic Performance Analyzer, we have some code samples, some software development kits, so I'm pretty sure you all can benefit from it. Also having some white papers and the forum I already mentioned. So a 24/7-hour forum where you can always ask us questions or exchange your experience with other developers. So, what I said. I would love to invite all of you guys, join the Game Developer Program, because the bigger the community, the better it is, and the more powerful we are. And I think we're living in great times, as I said. So let's work together. I think that's crucial. And let's create something great. And talking about something cool, I think it's time for Mike, overtaking the major part. So thanks a lot, guys. Have fun, and a great day.
Fantastic. All right. Thank you. So hello, my name is Mike Geig. I don't have a really cool picture of me, so I'm going to go back and pretend like this one's mine, because he's so dapper in this one. Wait a minute, there we go. So that's me. Well, no, when we were integrating slides, and I'm like, I can't compete with that. What am I going to do? So no pictures. So yeah, I work on the evangelism team at Unity, and we're putting together some pretty cool tools. And we want to, I mean, there are a lot of talks about ECS. There's a lot of booths and demos and a lot of documentation and stuff like that. But what we want to do is we want to provide a sort of foundational knowledge today to get an understanding of, okay, that's the code. It really looks really complex, but it's really cool and powerful. How do I get started? How do I start thinking this way? Because you'll see that this code is not hard, it's different. And that's way harder than being hard, right? Because it requires you to shift the way you think about data and processes and stuff like that. So let's start talking about that. And let's start with an overview. And so I'll often say classic, the classic way, the traditional way. What does that mean? Well, when we're talking about classic and traditional, and by the way, don't worry, this isn't all PowerPoint. I will actually show code, and we'll be in the editor and do some cool stuff, but I just want to build a foundational understanding. Classic is mono-behaviors, game objects and mono-behaviors. Our data and our process is coupled together on these scripts. These scripts are modularized, it can be put on anything, and that's what we have. And these mostly depend on these reference types. Transform is a reference type, right? Your rigid body is a reference type. Your scripts are reference types. And there's some good things and some bad things about that. And so here's just a couple examples, like your classic, your bullet, your player, some scripts, some components, whatever. But classic has some problems. So as we just said, there's reference types, and because it's a reference type, because game object itself is merely a container of references to other memory locations, which are then references of other memory locations, our stuff is all over the place. Your one player object can exist all scattered across the memory. Right? And that becomes a real issue when we need to move those objects, that data, into like our fast L1 cache so the CPU can do some processing on it, right? Also, because everything is scattered, we can't utilize things like prefetch. We can't do just a lot of these CPU optimizations that make our games a lot faster, right? And it becomes slow, very, very slow. Another issue is that we're often processing way more data than I need. All right, if I need to move something, all right, all I really need is the speed it's moving, its current position, and its heading to say, okay, well, now it's there, right? It's easy enough. However, traditionally speaking, if I'm using a transform component, I'm getting a bunch of stuff, right? I'm getting all, I mean, these are a list of some of them, but there's actually 3 times that many that I just couldn't fit on a slide. And all of that is being moved into our cache, which means it's moving out other data that I may need next frame, which means that data then needs to go get fetched again at the beginning of the next frame, and so on and so forth, and it's a big problem. Also, these tend to be one at a time, all in a single thread, and obviously that becomes very slow and it bogs our system down as our main thread gets blocked by all these Monobehaviour updates. And we're going to see this in action. So this brings us to things like the job system. The job system, which is out in 2018.1, where basically it allows us to very easily write thread-saved code. Anyone here raise hand if you've done multi-threaded code, not necessarily in Unity, just in general, multi-threaded code. It's a pain in the ass, right? Because all of a sudden your game's slower, and you don't even know why, right? And all of a sudden you have like these thread safety issues, and data becomes corrupted, and you've no way of figuring it out, right? And so the job system is going to make this stuff very easy. As you're going to see, you won't have to know anything about multi-threading. You focus on your code, and the job system handles making sure everything is thread safe, there are no racing conditions, all these super important things for us, right? It allows us to take our behaviors off of, a whole bunch of objects and process them in parallel. We also have the entity component system, which is a bulk of what we're talking about today, ECS, all right? And this is a big paradigm shift. It has entities, components, and systems, right? So an entity is basically nothing more than a loose handle to data. An entity handle is used to just find some sort of loosely related data components. The data components define what our things are. Right, so this is a very simplified example, but I might say that to me, a bullet is nothing more than some data for rendering, some data for positioning, and some data for spawning, all right? And when I say data, I mean data. I don't mean any process, right? Rendering data might just be what mesh is it, what material is it. Not how to render it, it's not relevant. What the data is, and that's it. Now, we have these systems then, and the systems have a query. All right, and the systems don't care what they're processing, but say like our health system. Our health system will throw out a query and say, find me every entity that has health data. I don't care if it's a player, an enemy, a bullet, does not matter. And I'm going to process just that data. Find me something that has render and spawning, and I will spawn it. Find me something that has render and position, and I will render it. What it is irrelevant, all right? We just define how we render something, how we move something. And what we're going to find is that most of these processes are the exact same always. Right? What does it matter how the player moves versus how an enemy moves versus how a bullet moves? Chances are, no matter all your theoretical complex behaviors, it all boils down to a transform.translate or a rigid body.move position or something of the like. They all tend to be mechanically exactly the same. And so why not cut out all the junk and just build a system that addresses that in a very, very fast way. All right, and that's what we're going to see. All right, so those are my slides. Let's get into Unity, and let's try this out. And so what I have here, and my mouse fell asleep. I have a simple scene here. This is from the 2D space shooter we have on our Learn site, whatever, and I'm in what I'm calling my classic example. And as part of my classic example, I have a couple scripts here, a prefab called my enemy ship, and this has a renderer on it, and a movement script. This is our classic example, right? Monobehaviors, game objects, prefabs that I'm instantiating, which a lot of you are already going, don't instantiate a bunch, because garbage collection and stuff, and trust me, I hear you. And I'm going to run my profiler while we're doing this, and we're going to see kind of what happens, right? So I'm going to hit play, and with this, I'm going to hit space to generate some more. And so let's just see how high we can get. It's also, my laptop is already super hot, so we'll probably have kind of low performance today, but we'll see. And I'm aiming at about 30 frames a second, just because, at 60 it's hard to tell, and I already went over that. So we'll say about 10,000 of these will put me at about 30 frames a second, which is good, right? 10,000 is game objects is decent. It's actually way more than we'd normally want for a game of this type, so like a bullet hell game. But what we're doing is just instantiating real 3D ships, so not 2D, whatever. These are meshes with a material that's being rendered, and we're just saying, all right, we've got 10,000 of these on the screen, and let's see what's happening. And so in my profiler here, I can see how fast this is running, and I'm using the timeline view of the profiler. So a lot of you are used to this view here, where we can just see, all right, script behavior is about 30% of everything happening. And let me just hop over to timeline, where I can see that, okay, so update.run script behavior, where we're basically processing all the ships, is sitting at around 12.7 milliseconds for 10,000 objects. So not terrible. So 12 some milliseconds for updating all my objects, and the rest of the time is spent on rendering or waiting for the update cycles or whatever. Okay, so that's our baseline. And if I want to look at this code, I'll see that the movement script is nothing super spectacular, where we have some update method. Update method is picking up some what's my current position, and then my position plus equals my forward vector, my speed. I'm storing all these things on my game manager because that's often how you do it. You just sort of set up all your criteria in one spot. And then time.delta time, I'm doing some bounds checking. If a ship goes beyond the bottom of my screen, just move it back to the top. And then I'm just writing that to the transform of the ship. So there we go. Easy enough. The game manager, this is going to be a staple. Every one of these scenes are going to be set up the exact same way. So the game manager has this region game manager stuff that is the exact same variables and values on every single one of these. Just, hey, that's the top bound, the bottom bound, left and right bounds. That's my prefab, that's their speed, whatever, right? So just your general stuff. And then in start, I'm just going to say, all right, add some ships. In update, if I press space, I'm going to add some ships. And then the actual adding of ships is traditional, right? I'm just going to say, all right, well, let's pick some random spot and let's instantiate, an enemy prefab ship, and then it appears on screen. Fantastic, right? So nothing spectacularly different there. And so, okay, so that's our classic, that's our baseline, 10,000 objects around 12.7 milliseconds. So let's go to the job system now. So I'm going to open up my job system scene, and this is set up the exact same way. Same game manager, same variables. It has a prefab with a mesh renderer. This time, no monobehavior, though. I don't have a script on here to move it because I'm going to handle this as a job. And I'm going to serialize or parallelize this across a bunch of threads. All right? But otherwise, it's the exact same thing. And if I look at the code, the first thing I want to note, again, no monobehaviors. So instead, what I'm going to do is I'm going to define a job. And a job has two parts. A job has the data the job cares about and what the job does. So data and processing as a job. Now, since it will not run on the main thread, it will not have access to most of the Unity API stuff. It doesn't know about time.delta time. It doesn't know about transform.forward. It doesn't know about these things, all right? Because it's on its own thread, right? It has no concept of frame timing and stuff like that. So we're going to set it up just a little bit differently. So this is my movement job. And so I have a movement job. That's its name. It's a struct, okay? Non-reference types. We don't use reference types in jobs. Already makes it better for memory. And it is implementing iJob parallel for transform. That's a long name, so let's break that down. So any job is an iJob, interface job, okay? Simple enough, any job is. If I call something an iJob parallel for, instead of taking my job and putting on a second thread, I'm going to take my job, break it up, and set it across multiple threads. Right? That's where I'm processing a large collection across multiple threads in a sort of parallel for loop. And then we have this special version called iJob parallel for transform, where we know we're dealing with transforms, so we're going to send that out across multiple threads specifically to read and write transforms. All right. The data that I care about is the move speed of my ship, the top bound, the bottom bound, and I have to actually give it delta time because it doesn't know what delta time is. It has no concept of that. Finally, since it's a job, it has an execute method, and because of the type of job it is, it's going to read in an index that it has because it's a parallel for job, and it's going to read in this special type of transform called a transform access. It's just like your regular transform, except all the reference stuff has been gutted out, and it's just your position, rotation, scale, pure transform data, as opposed to all of the other things that you don't need. Inside, the syntax might be slightly different, but the concept is the same. We're going to grab the position. We're going to multiply your speed by your delta time, by your forward vector. We're going to do some bounds checking, and then we're going to send it back. Inside our game manager, we do have now this transform access array. It's a new type, high speed, specifically made for jobs. And we're going to say, okay, when this is disabled, since we are using these new types, they're high speed, they're thread safe, they're great, but we have to tell it when to dispose. Otherwise, it won't dispose on its own. So there's a little bit to that. And if you don't, the editor will be like, hey, you didn't dispose this, so do that. And then you just do. Inside start, again, we're just going to, well, first off, we're going to create our array. We're going to add some ships. Update gets a little bit trickier, because here's the same, like if I press spacebar, add some ships, but inside update, first thing we're going to do is we're going to call moveHandle.complete. This is a handle to our job. Remember, our job is on some other thread, right? So we have to say, hey, job, are you done? Hey, job, are you done? Hey, job, are you done? Or we can say, you know what, job, finish right now. I'll wait, you finish. And that causes the main thread to wait a second until that job finishes. Usually they're ready about the same time. You might think, well, that's not good. That's useful when you have jobs that you need to keep in step with update, right? Otherwise, you have to keep pulling, are you ready, are you ready, are you ready? This way you just be like, you know what, you're ready, now let's go. All right, you don't do this if you have a whole bunch of different jobs, but in this simple example, it's a nice and easy way to keep things synchronized. And then we declare our job, all right? So I'm going to create a new movement job. I'm going to pass in the speed, the top and bottom bounds. I'm going to pass in time.delta time, and I'm just going to schedule it. So move job.schedule, and I'm going to pass in the transforms that I want it to process. I'll store that handle. Now, when I schedule a job, it won't start right away. It'll go into a batch that's being scheduled until I schedule enough jobs, and then it starts. Or I just say, you know what? There are no more jobs, stop waiting, just go now, and then it goes now and starts processing. Our add ships method is mostly exactly the same. We are going to call moveHandle.complete because we don't want to add ships in the middle of an update or in the middle of a thread. However, again, I had said it's thread safe. So if I did add new ships while it was processing, it would not break. It just wouldn't process those ships until the next time around. And so we just want to handle that. We want to finish it and then handle it. But this is the same, random position. We're going to instantiate it, and the only difference is now we're going to add it to that collection that every frame we're going to say, hey, process these ships, process these ships, process these ships. Now, as a result of doing this as a job system here, so I had said before that we wanted to be around 10,000. At this point, I'm at 21,000, so I'm already way above that and still around 30-some frames a second. That'll slow down as they all come on the screen here. So we were about 27 frames a second previously anyway. And I'll go to my profiler. Let's take a look at it now. So first off, now that I'm on my profiler, so I'm coming here, and I'm going to notice that there is no, basically a monobehaviour update, a script behavior update here. Remember before it was 12.7 milliseconds. Now it's gone. But if I look to the left here, there's the Unity job system, and I'll expand it here. And here it is. So let me zoom way in. And I'll see that my movement job now, total, is still 12 point whatever milliseconds. It was 12.7 before, it's 12.3 now. However, that's total if you add up all of the threads. Each thread has a 0.87 millisecond overhead to process this across 16 instances. So it broke this up, spread it out, and each batch takes 0.8 milliseconds to process for a total of 12.3 milliseconds, but much, much faster. I had to zoom in quite a bit to actually see that section. And so that's pure performance. And this is even with 21,000 as opposed to, I forget how many I had last time, like 14,000 or 13,000 or something like that. But you can see here, now we're up to 21,000 because it's pure performance. Right? It's breaking it up and whatever. And so that's the job system, okay? We still have the same memory overhead, right? We're still, dealing with instantiating amount of behaviors, reference types, high memory overhead, potential garbage collection, but we are processing the behaviors a lot faster. So now, let me move to the next step. Let me move to entity component system. So let me open up that scene here. And we're going to see that this is going to be slightly different, but again, we're going to have the same GameManager. All right, same all that stuff set up. I do have a prefab here, but it's not actually a prefab. I mean, it is a prefab, but we're not going to use this like a prefab. Instead, if I look at it, there's no mesh render or anything like that. Instead, we have these components, these data components. So I have a rotation component. Oh, thank you. I have a rotation component, and all that does is it stores a quaternion. I have a position component. All that stores is a float 3. There's no processing. I'll show you here in a second. A transform matrix component, a mesh instance renderer component, and a move speed component. Most of these components are built in. I did write the move speed component one just to show you how we write a component. But what we're going to do is we're going to take this prefab almost as if it was a template. And at runtime, we're going to strip the component data off it and create entities out of it. We'll never actually use this as a game object, as a prefab, anything like that. So let's take a look. And so First thing I'm going to do is I'm going to talk about a speed component. It looks like this, move speed component. So it's move speed, implements iComponent data, all right? And it has some data, public float value. Now you might think that's a lot of work for just a float, but it's crazy fast, as you're going to see, and memory efficient. So we've got this public float value, and value is just sort of a thing, sort of a standard we do, or just whatever is inside a data component, just name value. We have this line here, which is completely unnecessary. This line specifically says, I could add this component to a game object so that I can see it in the inspector, which is how I'm using it. But if I wanted to just add this component at runtime or just via script, wouldn't need that at all. So really, a component is just public struct, move speed, iComponent data, and the data. If I wanted to use these data components as like tags to help with my querying and stuff like that, I could just not even have any data. I could just have public struct, maybe public struct disabled object of type iComponent data. And later, when a ship gets blown up, I just put a disabled object component data on it, and I have some query that, as it's rendering, just says, like, if you have a position and a rendering and not a disabled object, I'll process you, all right? And then all of a sudden, they all disappear, okay? So we can use these components for all sorts of stuff. From the components, so I've got these objects with components, I need to define a system. So entity might be my ships. Components, right, are these data components. Let's talk about a system. So here's my movement system. If my movement system is of type component system, and as I had said in the slides, we have a query, right? What does this operate on? Well, this is going to say, find me all entities that have a position, a rotation, and a move speed. And that's what it's going to do. Find me everything with position, rotation, and move speed. That'll get returned back, and it processes it. This public int length is just a helper. If you have it, it'll get filled with how many objects fit that query so that you can iterate through them. And then we have this sort of special keyword inject, which basically says, take the results of that query and put it in this struct. Put it in this variable for me. So that every time this runs, every update, it takes that query and stores it here, and takes that query and stores it here, right? Updates it. If you're ever looking at code and you're like, well, which one's the query? Which one's the filter? How do I know what this is processing? Look for the inject keyword, the attribute. You see inject, you're like, that's it. That's the query, right? This is the query. And you'll notice that these two, rotations and move speed, are read-only because we don't need to change them. So we'll just make it simple, make it safer. Right? So positions is the only one we change, and we store these in a specialized new container called a component data array, which is very fast, which is very thread safe, very efficient, all right, for processing these things. So this is my, my query, what the system is looking for, and then I have a method on update, protected override on update. Every system has one of these, and this is where we process our data. So here I'm going to say, okay, for int I equals 0. I is less than enemies.length. If I didn't do that length variable, I could have just did, enemies.positions.length or whatever to find it that way. And I'm just going to iterate through. So what's the position of this ship? What's the rotation? What's the speed of the ship? And then this code is the exact same as we've been seeing, slightly syntactically different again, but position.value this time, plus equals time.delta time. We can use references again because we're back on the main thread with this system. This isn't a job. This is a system here. So we can do time.time or delta time, speed.value, math.forward. We have a new math library, by the way, that math.forward. Crazy fast new math library, so it's awesome. Math.forward, and then again, we're checking our top bound and bottom bound, and then just setting the position of our ships. GameManager is a little bit different. So we still have all the GameManager stuff. That hasn't changed. But we do have this new Entity Manager, all right? And at the beginning, we're going to say, hey, world, active world, if you're listening, I'd really like an Entity Manager, please. And it will find the active one. If there isn't one, for whatever reason, it will generate one and give it to you. Update goes back to being, hey, if I press spacebar, add some ships. And then inside my add ships method, this gets a little bit different. So now, remember, because we're using that prefab, that game object as a template, we're going to say, all right, let's create a native array named entities of type entity. and we'll just set it to the amount that we're trying to spawn. And we'll say this is a temporary allocator just for efficiency. The types of allocator are invalid, none, persistent, like I want it to last, temp, or temps is going to be temporary for a job. I don't actually know why anyone would ever create an invalid memory allocator. I probably should ask the team like what that's about, but whatever. And then we're going to say, all right, manager, this entity manager, I want you to instantiate some entities. All right, I want you to put the references in this native array I just created for me. So all this does is stores references. This doesn't store any data, just handles. Right, handles to where the data is located. And what am I creating? Well, I'm not creating enemy ship prefabs, but this is my template. Strip all the components off of it and build me an entity that has those things. That's what it's doing. So it's not making a game object, it's making an entity from that game object. So that in Unity, in the inspector, I can just easily drag and drop, oh, I want this component, this component, this component, just visually. And then this is going to take all that and build it. By the way, real quick here, just as an aside, every unique collection of component data, so in this case, my ship is a unique collection because it has like a move speed, a rotation, a position, a transform matrix, and a mesh renderer, right? That's one set. We call that an archetype. All archetypes get stored together, tightly packed in memory as struct data, so that when it's time to process them, our CPU can prefetch all the way down that array. And so as it's processing, the data is already ready in cache. It's because it's all just sequential. And you're going to be processing them all at the same time because that's how the systems work. Super fast, as we're going to see. So then I'm, again, generating some random position. And now I'm going to say, hey, manager, I want to set some component data. You remember this entity you just made? Well, I want you to give it this position. And hey, I'm going to set some more data. Hey, remember this entity? I want to give it this rotation. I want to give it this move speed. Now, I could keep this array of entities if I ever wanted to access these entities again, like, oh, hey, I need that handle. Where is that handle at? But in this simple example, I don't. And so for memory management, I'm just going to dispose it. What this means is I can't then programmatically go get that object again, but I don't need to in this example, so it's fine. And so let's see the result of this hard work. So here's my ECX example. We were at, 21,000 last time. Let's run it again. So now we're at 20,000. We're a little bit faster than that. We're not going to see much performance. Honestly, we should be seeing maybe double or triple performance. But my laptop is very hot, so I do apologize for that. And I'm also getting GPU bound at this point. So it's not even my CPU anymore. And I'll prove it to you. Let's look at the profiler. So let's run this here. And so before we were saying that it was about 12.3 milliseconds total. However, each individual thread when we were using the job system was like 0.8. Well, as I come back here, I'm going to see that, okay, this is a bit slower again. Here's my move system. All right, it's actually slower, but everything else will be processing faster. So my rendering will be faster, everything will be faster. I know you can't see it because I'm GPU bound and my system is hot, but I really should be seeing about double of this, so I do apologize for that. But this will be a little bit slower because, again, it's back to being all on the main thread, right? And so it's not jobified anymore. So it's one chunk of time, but all of our other stuff, like we can see some of our other rendering and stuff like that, now happening through the ECS system. And so the instance renderer, all of these are rendering in 1.2 milliseconds, where before that was significantly higher. We're also at a fraction of the memory cost. All right, so I didn't benchmark earlier, but if I'm looking at the profiler right now for this anyway, and I'm looking at my memory costs, I'm looking at 201 megabytes of memory used for 21,000 of these entities, which if I was doing this with the classic, with the job system, I'd be sitting around like 1.5 gigabytes. All right, so significantly less memory, and most of our processing will be much, much faster as a result. So that's cool. That's classic, that's job, that's ECS. But that's not where we stop. Let's do ECS with jobs. All right, let's take it to the next logical example. And actually, real quick before I do that, I'm going to hit play again. And I'm going to show you this new window we have, the Entity Debugger. And what this does is it shows me all of my systems. You'll recall that I showed you this system, this movement system here, but I didn't add it to my scene. My scenes are exactly the same GameManager, same everything, right? So why is this running? Well, it just runs. Just by virtue of that code existing in my project, it is a system that operates, and it says, does anything match this query? If it does, it turns itself on, and it just becomes a part of the engine, just how things work. And if nothing matches that query, it just doesn't. So I have here my mesh instance renderer. That's what's rendering all of my stuff. Here's my movement system job. And remember what my query was? Find me everything with rotation, with move speed, and with position. Position is read-write. Rotation and move speed were read-only. How many entities did it find? It found 20,000. And is it running? Yes, it is. So I can use this to see all my systems. I can see, if I wanted to, every one of the entities, every one of the 20,000. I can say, hey, entity 116, what are you up to today? Well, entity 116 is just chilling here, moving on down the z-axis like we wanted him to. And, that's all the stuff that entity 116 is doing, which, Entity 116, he's going through a real rough time right now, so I just wanted to give him a shout out. But yeah, if I wanted to, I could say, what happens if I just don't move these guys anymore? Okay, fair enough. We'll just disable that move system there. But, so it allows me to debug some stuff. We're adding a whole bunch more tools for that. All right, I wanted to be sure to show that before moving on. So let's take a look now at ECS with jobs. So we're going to be using the same move speed component data. This is going to be set up the same way. We've got a GameManager. We've got, again, a prefab that we're using as a template. All right, so that's not different at all. It's going to have the same components, the exact same data components, so including this move speed here. All right, so all of that stuff is exactly the same. But it's going to have a different move system. So if I click on my move system here, now I will see that it is a job component system as opposed to previously where it was just a component system. So it's a component system that works with jobs. Job component system. And so here's my job. As we saw before, we create jobs that are structs. So there's my movement job. And instead of having a query that looks like this, struct, enemy group, these things with the inject, with this system, my query looks like this. This is an iJob process component data with my query. Find me everything with position, rotation, and move speed. Find me all entities that match that pattern. And then I'm going to define the rest of my job. Well, what else do I care about? I care about these things. I care about position, rotation, and move speed, sure. I also care about my top and bottom bounds. And I care about delta time. Because again, we're back to being a job, which means we're back to no references. We're back to not knowing what time.delta time is or any of those other Unity reference API things, right? So now we're back to needing to give the job the data that it needs. My job has an execute method, just like all jobs do. And here I'm going to read in my position, my rotation, and my move speed. These two as read only, just like previously. And I'm going to process this exactly the same as before. What's my value? Value plus equals delta time times my speed times my forward vector. Check my bounds, apply it back. Same algorithm, again, slightly different syntax. So this is my job. That's my self-contained job right there. And again, since it's a system, every system has a protected override job handle on update or just on update, whatever the return type is. It's going to read in some input dependencies, and I'm going to create a job, just like my previous job system example. New movement job. This is my top bound. This is my bottom bound. This is my delta time. Hey, move job, I'm going to schedule you. You're going to run with this system. And this value, 64, this means that I'm going to break it up into batches of 64. All right? Generally, you'll want heavier computations broken into smaller batches and easier computations or larger collections broken into bigger batches. But I found that this example is so simple that this number really didn't matter. Right? I could go big, I could go small. It didn't impact performance like at all because it's a very simple, I'm just moving something. That couldn't computationally be any simpler. I'm not even rotating it, I'm just moving it, which is crazy simple. So that number doesn't really matter. And then it's going to use this input dependencies to see if it has to wait. This is how the system manages timing to make sure things run in the correct order and can rely on each other and whatnot. and that's going to return that move handle. The game manager is actually going to look exactly the same. Get me an entity manager, set my stuff, dispose my entities, whatever. That has not changed at all. So let's run this one. Let's take a look how high we can get. Again, I'm GPU bound, so I'm not sure how high I'll get there. Actually, I'm doing all right now because all this rendering stuff is going to be simpler. So now I'm I'm on a laptop too. So we'll say 51,000 puts us at 30 frames a second. So we went from 10,000 to 51,000, so that's modest. And let's look at my profiler here. Let's just grab a frame, grab one of the new frames here. Right there. All right, so let's see what we got going on. So I'll zoom in here. And again, we're not on the main thread anymore. The job isn't here, or the methods aren't here. They're down here. And I'm going to say like movement system. All right, so now we've got 8 instances. I am processing 51,000, right? Yep, 51,000. Total time is 18 milliseconds. That's total time. But my individual threads are 2.4 milliseconds. All right? So again, 10,000 at 12 milliseconds to 51,000 at 2.4 milliseconds. I know which one I like. All right. Now, that's great. It's huge performance. But there's one last thing, right? One of the reasons that we're kind of excited being with Intel, right? And all this cool new modern hardware. We're talking about scaling CPU performance. Why treat every CPU exactly the same? Just, hey, process this data, process this data. All these new CPUs have these variances, how they operate, how they handle different math functions, all these different built-in things to make them super fast. And one of the cool things coming up later this year is something called our burst compiler. Now, the thing about our burst compiler is it's specifically built to take advantage of all those cool inner workings on all of these different CPUs. And the best part about it is you don't write any code to make it work. So I'm in this scene, I'm in this example. What I'm going to do is I'm going to go up to my jobs menu, and I'm just going to turn it on. That's it. So let's see what we get. We probably won't get more objects because I'm CPU or GPU bound, but I'll show you the profiler to prove that it's doing something. So let me just turn this on here. Let's see where we get. We'll probably get to the same 51,000 at about 30 frames a second. A little bit better, but still, like I said, GPU bound. So let's grab one of these frames here. And now, let's see. So before 51,000, we were at 2.4 milliseconds per thread, right? All right. So let's take a look. 0.45 milliseconds. I know, that's stupid, right? So, yeah. What this means, we did a talk like this at GDC this year, and Intel gave us an i9 processor. I didn't even know it existed at the time, which was awesome. And we went from initially being able to do 12,000 of these ships to 350,000 of these ships simultaneously on screen. It was stupid. But it was like the most insane bullet hell game of all time. But that was it. I didn't do any extra code. I just turned it on. I said, oh, yeah, please take advantage of CPU resources. And it's like, all right. And then, boom, crazy fast. And now you might be thinking, why would you ever build a game like this? And we're not really talking about building a game like this. We're talking about, look, maybe you have a VR game, and one very small part of your VR game just slows you down and makes you lose frames. I built a katana game where I'm slashing up robots, and every time I do, that algorithm was kind of slow. Convert it to ECS. That bit makes the whole thing faster. Maybe I'm making a mobile game, and I don't need to add insane number of things. I just want more performance, so I'm using less battery. I'm using less CPU. I'm generating less heat. Maybe I just want performance for performance sake, right? Maybe I want to script giant space battles. That's one of the things we did in here. So if I leave this scene here and I go over to one of our other scenes, the folks at Intel built this one, and it's just a space battle where I'm still playing a very simple game here, just shooting and stuff like that. But behind me, we have all this stuff going on, and I know it's kind of hard to see, but these are all 3D objects, all shooting ECS bullets at each other and blowing each other up with ECS and collision detection, and it's all real, non-prescripted, all procedurally generated on a laptop while I'm just playing my simple game experience, or whatever I want to do. So there's so much we can get out of this, and it's not hard It's just different, right? And eventually this will just be the way, right? Because there's so many pluses to doing this, and it's procedurally so very sound. So I encourage everyone to try it out. I know we're just about out of time. If you have any questions, please use the microphones. But otherwise, thank you both very much. Let me put up our contact information. And I appreciate you all coming out right after the party night and being here with us. So thank you all very much. And again, if anyone has any questions, please feel free. Come on up. We're recording it. We'll say hi. Or not. You know, that's cool too.
You definitely also have to apply for a Wednesday session the next time, right?
Yeah.
Really appreciate that all you guys are here.
Yeah.
After that party.
Python also takes advantage of mobile processors or only desktop?
It will. I can't verify. So it's sort of a preview right now, being released sort of later this year. So as of right now, I can't verify yes or no, but the plan is yes.
Okay, thank you.
No problem. Hi.
Hey, that was super cool. Thanks very much. The entities that you created, they were kind of shown in the entity debugger thing, not game objects in the scene.
Yes.
Can you mess with them and move them and stuff like normal game objects, or
So,
are they kind of locked away?
Not yet. So it is, I mean, it is a preview feature. It is something to experiment with and kind of start thinking about where we are getting. Our plan is to get all of our tools to, eventually we'd like it so there was just no difference between game objects and entities visually for the end user, you know, cool. But the tools aren't there yet.
So I guess, do they even show up in the
They don't show up right now in the hierarchy. The goal will be for that to be the way, but just right now we use the entity debugger and stuff like that.
Cool, thank you.
Yeah, no problem.
Hello, and thank you for the presentation.
No problem.
I just want to ask, are there any plans to use the entity component system and the job system for things other than transform, like searching maybe databases or using Vuforia or implementing all these kinds of stuff that take a really long amount of time?
Absolutely. So, I mean, I use transforms, but literally any data processing. Like I said, slashing up meshes. Any process that I can say, okay, well, this is the data of it, and this is what happens to that data. Absolutely. Searching, mesh generation, plane finding, anything.
Thank you.
I think we're running out of time. So.
Thanks for the great talk. My game is very instantiation bound because it makes a huge CPU spike.
Absolutely.
And does the entity component system, it looks like that reduced it a lot. And does multi-threading also help, or what makes it better for instantiation? So should I use both, or?
So and this will probably be our last question, but you can obviously find this right afterwards. But so the entity component system, it's dealing with struct data only. That's all tightly packed, which, you know, even at the end there when we got up to, I forget what we got up to there, but still probably only like 250 megabytes, as where that many objects without was probably be like 3 gigs of RAM or whatever. So I mean, just because we don't have all this extra data, it's not references, it's not scattered, we're not looking for special bits of contiguous memory, it's all just together in one spot, highly compact down. It makes it very simple to instantiate at runtime with very little to no impact.
Nice. Yeah. And can I even do multi-threaded instantiation?
I'm sorry?
Can I even do multi-threaded instantiation with a job system?
Probably. I've not personally tried it, so I'm not going to say yes, but I'm not going to say no. But we can find out. I guess I've never actually tried, but I don't see why we couldn't.
Okay.
Yeah. Actually, I know we can. Yes, we can, because we have another example that does that. We got to close up here, but I'll just come right on out and we'll answer questions right afterwards. I'll be there in just a moment.